Hi, and welcome to the MedTalks webinar series where you can learn from scientists, entrepreneurs, industry experts, and healthcare professionals who are all driving for progress in healthcare today across the globe. I'm Andrew Adaby, and in this episode, we'll be joined by our guest, Ed White. Now, Ed White is an experienced professional with over 30 years experience in medtech, digital health, and also clinical research. His passion for innovation has driven him in his success across those sectors. Now, in this week's episode, we'll be talking about the cutting edge of technology, which is organoid intelligence, OI, as opposed to AI. Today, we embark on a journey through the complexities and revolutionary prospects of OI, from its initial conception to its profound implications across various domains, including medicine, ethics, and even space exploration. Our discussions will deep dive into the pioneering science, the challenging ethical dilemmas, and the potential societal transformations that brain organoids bring to the forefront. Now, let's prepare to explore, question, and understand the responsibilities we hold as we stand on the brink of these significant scientific advancements. Let's engage. Hi, Ed. How are you today?
I'm very well, Andrew. How are you doing?
I'm very well, thank you. After the intro, I'm very keen to dive straight into my questions for you today. And I think the first question needs to start with, current brain organoids. How do they actually mimic real human brains in terms of structure and function, and maybe what are some of the similarities and differences between the two?
Sure. First, let's break down what brain organoids are. So scientists today create them by taking human stem cells and coaxing them to develop into 3D structures that mimic aspects of our developing brain. While they're not perfect replicas, organoids contain many of the cell types found in our real brains and even actually form layered structures similar to our brain cortex. However, I think, Andrew, it's important to understand the limitations of brain organoids. So, for context, our brains today weigh about 1.3 kilograms, while these organoids are just a few millimeters in size. And in addition, they lack what we call the intricate neural circuits and connections that enable the sophisticated functions of our real brains. So we got to think of this as kind of like a brain development 101. They got the basic building blocks, but aren't quite ready for that advanced cognitive task today. However, despite I think these limitations that we see with these brain organoids, they do allow us to study the early stages of the brain. So, for example, researchers today can observe how neurons are forming, migrating, and connecting in real time. So, if you think about neurodevelopment disorders like autism or schizophrenia, these pretty much originate in these early stages. And the other thing about organoids today is they're a much more ethical and accessible alternative to using human brain tissue. We don't have to rely on post-mortem studies, samples, or animal studies. Researchers can grow and manipulate these in a lab. So this opens up a whole new way for drug testing, for example.
So going from a few cells to more complex tissue to a full brain, that journey seems immense. Now, there's going to be some significant technical challenges in creating larger, more complex brain organoids. Now, how can the community overcome these hurdles?
Yeah, so one of the biggest challenges for scientists today is the nutrient oxygen delivery. Unlike our brains, where we have an intricate network of blood vessels to keep ourselves nourished and oxygenated, brain organoids lack this crucial infrastructure. So as a result, what happens is that the large organoids often die off, putting an upper limit on their size. One of the ways that scientists can overcome this challenge is what we call developing these things called microfluid channels. So they act almost like artificial blood vessels. So you can deliver these nutrients and oxygens to these inner cells, which were dying out. So by carefully designing these channels and optimizing like the flow rates here, researchers can create much larger, healthier organoids that can survive and like actually thrive in the lab today.
So, overcoming that challenge to improve the nutrient flow, we get to a point whereby we can increase the amount of organoids, more complex. Then you get into the realm of consciousness, you get in the realm of sentience. Now, then you're going to get into ethical questions of How do you manage this? How do you make sure you regulate this? What are your thoughts and what's the research that's been done so far?
Look, Andrew, the question of consciousness and brain organ is not something that we can easily answer today. But I think we definitely need to think about it very carefully and hard about as these organoids get more and more sophisticated, what's going to happen. Right now, the most advanced organoids today, there's a very slim chance, second to none, there's any sort of consciousness going on there. But here's one thing. We're seeing today more architectural complexity with these organoids. And we start hooking these organoids up to sensors and computers for learning. We can't rule out a possibility of some sort of sentience emerging. That's why I think it's so critical for us today that we have like clear guidelines based on what we know about the brain and when we can spot artificially grown brains where they might start to become conscious in the future.
So it sounds like at the moment that there's a clear lack of tests for consciousness. Now, how should we think about the possibility of sentience emerging in organoids as the technology actually progresses in 5, 10 years?
Yeah, yeah. So consciousness is one of those biggest head scratchers in neuroscience. We're still very much in the dark about the minimal neurocircuitry and activity patterns that are needed for subjective awareness even to emerge from our brains. So figuring this out in organoid we're in a bit of a dilemma. So we don't have any really kind of definite markers today to look for. I think the safest bet is that if they start showing advanced brain-like functionalities, it's kind of like saying if they're very complex neurologically, the more that we consider, there's a possibility that there's some sort of sensation emerging from that experience there. But here's the thing, I don't think we can just sit back here and wait for this to happen. We actually need to be very proactive today already and take because the science will advance here. And we need a team to get this addressed, the neuroscientists, the policymakers, the ethicists, and us, the general public. We all need to put our heads together to figure out how to navigate here in this pretty much uncharted territory.
So there's going to be some rules and regulation and governance that are needed for oversight for the ethical development of brain organoids, whether that might be in medical research and in commercial applications, I believe. What's your thoughts on that?
First off, I think we definitely need to have dedicated committees that include both scientists and ethicists to really scrutinize these research proposals, especially when it comes to experiments at making organoids a whole lot more complex. These committees, for example, can take a close look and then they can put extra limitations on if needed. Secondly, I think it's really high time we establish clear science kind of base guidelines that spell out how advanced an organoid's neural development can actually get before we start putting some regulated protections in place. And hey, we can always update these guidelines with the science as it evolves. So, from the commercial side, for purposes, I think we've really got to be clear and have social responsible business practices in place. We can't have a situation in our society where the most wealthy have access to potential clinical innovations or where the organoids are used for questionable misuse neuroenhancement applications. To me, that's just not right. But I think the real issue here is no matter what the regulatory frameworks are put in place, we got to make sure they're adaptable and we can get input from the public. Because as our understanding of brain organoids evolves, we can actually tailor our approach to regulating them. But at the end of the day, I think it's striking the balance. We want to progress scientifically, but at the same time, we got to have these ethical guardrails in place to keep those things on track. It's not going to be easy for anyone, but I think if we approach this with a commitment to scientific innovation, ethical responsibility, I think that balance will get it right, Andrew.
From my standpoint, and maybe some of my listeners, I don't think there's a competition between OI and AI. I think actually there might be a convergence of OI and AI. So can you see at a point in the future where they could have OI and AI working together to enhance learning and potential memory as well?
All right. I think here's the deal. If we want AI and brain organoids to really join force and take things to the next level, we got to focus on a few key breakthroughs. I think first and foremost, we need to develop more advanced two-way communication between AI systems and those advanced 3D neural cultures, what I call a kind of efficient digital biological interface. This means really pushing the envelope with these cutting edge electrode arrays that allow us to input complex data and observe those organoids' reactions in real time. It's kind of like giving AI a direct line to the inner workings of the biological brain. But for this partnership to work, we also need that AI that can learn and adapt on its own by exploring the feedback from those organoids. This could involve using brain-inspired computer chips that allow AI to crack the code of the organoid, neural firing pattern, for example, and gain knowledge through this hands-on experience. But I think ultimately, we want to create a symbiotic relationship between the artificial and biological intelligence worlds, where each bring the best out of both of each other. And I think AI can really help us interpret and influence the organoid computations, while the organoid's wetware could give AI a boost in terms of its flexibility and efficiency. But to make this happen today and make it a reality, we need, again, collaboration across multiple scientific disciplines. This will involve neuroengineering, AI, data science. Everyone's got to come together here to bring this and make this happen. But the potential payoffs could be huge. I think it will create a new computer paradigm out there and allow us to have even more insights into our cognition. So it's a really exciting space that we can't really ignore.
Ed, interestingly, you mentioned computing twice in your last response. This space will probably require a massive amount of computing power, quantum computing. Now, I'm sure this might actually give new insights into how the neural dynamics work. Now, how might this actually hold quantum computing change this space going forward?
Yeah, so don't get me started on quantum computing, Andrew. I love this space. Quantum computing and brain organoids could be a match made in heaven. And I'll explain why. Our brains are very complex, with billions of neurons doing their things in mind-bending ways. Supercomputers today might not be able to keep up with all that complexity, but quantum computing could be the key, I think, to unlocking the secrets of our brain. With quantum computers, we might be able to map out the exact state of those individual neurons and synapses as they're actually processing that information. So that's a new level of precision, and that's just not possible today with our supercomputing. And get this, quantum algorithms could even help us figure out the basic rules and principles that organoids use to learn and compute. We could discover, I think, actually totally new ways that brains process information used this kind of weirdness of quantum mechanics. So I think by applying quantum computing to brain organoid research, we could open up this mystery of how brain organoids work in ways that we've never had possible before. And I think the insights we would gain from this would help us actually in building the next generation of quantum computers that are more wired like our brains, super efficient, flexible, and able to learn. We're in the very early stages, I think, of quantum computing, but the potential here it's literally mind-blowing what we could do there.
This program will be going to all different platforms. Someone listening to this who hasn't got any science background might be listening thinking, my goodness, this all sounds a little bit scary. You can imagine that brain organoids technology could be potentially misused, Ed. Now, we really got to think about what steps could be put in place to prevent that from happening.
Yeah, it's a good question. So as you heard, brain organoid research is powerful, and that means it can definitely be misused if we're not careful. I'm talking about, let's say, an unethical company who may be strip mining organoids, for example, for data, or if you think of military applications for making biological or brain-based weapons. And look, let's just think about the privacy nightmare of getting a growing copy of a brain in a lab and all the issues around neuro rights, for example. But here's the thing, we shouldn't let risk scare us off with incredible potential here, in my opinion. We just have to be, I think, proactive about steering this research in a responsible direction. And it means putting in rules in place, I think, around consent, ethics, and security. And it means for us to keep a super close eye on the tech as it advances and hitting the brakes if things start looking a little bit sketchy in the future. And most importantly, I think it's an open, honest conversation we've got to have about this stuff with the public. There should be no more hiding this. We need to engage people on the real impacts, good and bad. It's actually the aim, Andrew, of a book that I've just recently written on this topic. So yeah, I don't think it'll be easy to keep this organoid research on the right path. But if we stay alert and ethical and engaged in a way, I think we can do it. And we can build actually really good future here with this technology. It's definitely worth the effort.
Absolutely. And I think organoid research should progress absolutely. And I think those who listening might see the benefits of that. However, there needs to be a real collaboration between the neuroscientists, the ethicists, and the computer science as well. What's your thoughts on that?
Absolutely. Brain organoid research isn't just a neuroscience thing or an ethics thing or a computer science thing. It's actually everything thing. As I said here in our talk, there's a lot of collaboration that needs to be going on here to make this breakthroughs done. And we literally need all hands on deck. Our neuroscientists to grow those organoids, the computer experts to interface with them, those ethicists to navigate the moral quandaries. So our collaboration is non-negotiable. And I think cross-pollination, you want to call it, of expertise and ethics is really essential in case otherwise this field will spiral out of control in the wrong direction. And I must acknowledge Professor Thomas Hartung from the John Hopkins and his team have done this in a great way. They set up this organoid intelligence community. And we just need more of this going on here as this progresses.
At the top of the program, the intro, we also mentioned space travel, completely left field, but how does space travel and organoids actually help in terms of space travel in the future?
Yeah, so I think right now we're getting more ambitious with space travel. We're already talking about sending people to Mars. But here's the thing, we still don't really understand that cosmic radiation, microgravity, and isolation can do to the human brain on the long haul. And that's a pretty big deal if we want to stay our astronauts sharp for long periods of time in space. And brain organoids are now starting to be used routinely for medical research in space. For example, they can help us understand neurological disorders right here on Earth. And we can see that scientists can see the process of aging and cell changes can actually accelerate in space. So there have been several space missions over the past few years researching into disease areas like Alzheimer's, Parkinson's. And the challenge is really to figure out how we can get these organoids alive and thriving in these orbits for longer. And I think actually, to me, it's the most exciting frontier for medical research at the moment.
As a final question, Ed, what are the kind of long-term goals of organoid research?
Yeah. So first off, I think on the basic science side, we got to get to work really on making sure that they can mimic the complexity of our human brain. I'm talking more like distinct regions of the brain where we have sensing, basic sensing and memory, a kind of brain in a bottle in a way that can set us up to probe the roots of our cognition. But it shouldn't just be a lab curiosity. I think we need to translate these breakthroughs into personalized treatments, accelerate the drug testing, and I think also to inspire potentially new kinds of AI. And of course, we got to grapple in this journey with the deep questions about consciousness and whether organoids could have a hint of inner life. But here's the key. I think as organoids grow bigger, so does our responsibility. We just need to be more proactive around the ethics to match this pace of progress. As I mentioned before, we need consent protocols, for donors, robust monitoring. For example, if there's any sign of an organoid suffering, and equitable access to this technology. This won't be easy. And I said time again, we need collaboration across the science, ethics, and society to keep this on the up and up. But I think the potential is staggering here. We can imagine actually in the end, Andrew, a world where neurological disorders are a thing of the past. We can simply grow and tweak this perfect brain model, or where our drug trials can become hyper efficient and we can actually do research without any animal involved. So it won't be easy, but I think it will definitely be worth it.
Ed, thank you very much for your time. It wasn't enough time. Would love to have you back again on Med Talks in the future to talk more about this fascinating space. Thank you very much for your time today.
Thank you, Andrew. I really enjoyed it.
Thank you for tuning into today's episode. If you enjoyed it, be sure to subscribe to our channel and share it with someone who might find it valuable. You can access this on TikTok, YouTube, LinkedIn, and X. We would love to hear from you. Stay in touch.